Friedel-Jacquinot. I am Emmanuelle Deleporte, head of this Fédération Friedel-Jacquinot. Alors, this federation is a new cluster of the Paris-Saclay University, containing 6 laboratories: FAST, LPTMS, LPS, ISMO, LAC, MIN, which are all located on the Petit Plateau in the same street. Our objective is to develop scientific interaction between these laboratories, of course, share some advanced equipment, promote interdisciplinarity, and be internationally visible and attractive for the best students. And a second objective, which is very important, is to ensure that the students get the most out of their scientific environment in University Paris-Saclay, in particular by visiting our laboratories, discussing with the researchers as early as possible in their course. We will organize 4 colloquium, it's the order of magnitude, 4 colloquium per year in the same shape. On different topics. The topics treated in our laboratories are related to matter, light-matter interaction, complexity of the matter, and so on. And we will choose different topics to vary the events. So now I want to thank several persons. First, I want to thank the graduate school physics for their help and welcome in this amphitheater. And I want also to thank the technical staff of this HPAR building, in particular Xavier Anselme, Lionel Trissard, Guy Manetti, Jean-Marc Fischbach, Nathalie Niwash also. I want to thank also Sophie Tourlet, which is assistant de direction of Fédération Friedel-Jacquinot. And some members of the LPTMS, Valentina Ross, for her help with the Zoom session, because we have also some persons who will be here by Zoom. And Raul Santa Chiara for the welcome, and also the organization of the visits in our laboratories by Sir Michael Berry. Thank you very much, Sir Michael Berry, to be here with us. It's a great honor. And now, please, Dr. Bogomolny, can you present with several words?
Thank you. It is a pleasure and a honor to introduce the first. It is a pleasure and a honor to introduce the first speaker of Friedel-Jacquinot Federation, who is going to speak about geometric phase, old and new. You all know that Michael Berry is a distinguished scientist working in different problems of mathematical physics. He got bachelor in '62 from University of Exeter. Then it's a PhD thesis he defended in University of St. Andrew in '65. His thesis advisor was Robert Dangle, who is known in solid state physics, especially, and also in asymptotic expansion, the subject which Michael will develop quite later. And his thesis has title diffraction of light by ultrasound, and somehow it anticipates his interest on the wave phenomena, which will be the main subject of his works. All his scientific career he done in University of Bristol, where he entered in '65 as a postdoc, and then follow all the stairs, a reader, lecturer, professor of Royal Society. From 2006, he is Melville professor in physics, emeritus. He works in many different subjects, starting from optics, ranging from optics to Riemann zeta function. And most of his works is somehow related with wave in different avatars, especially for the problems which are somewhere in the boundary between classical and wave description. As you know, waves are mostly has a phase, and Michael developed important knowledge which we'll have discussed today of geometric phase, commonly known as a Berry phase, and applied to many different problems in optics, in sound, and quantum mechanics, even for the swimming of the small animals. He is one of the father of quantum chaos, of semi-classical calculation for many-dimensional system, and actively participate in open all subject of this field, summation of periodic orbits, resummation of orbits, Riemann zeta function relation with prime and periodic orbits, pseudo-integrable model, quantum map, etc. He works a lot of wave singularities. He developed very carefully singularity of the amplitudes, acoustic, and the wave singularity as optical vortices and so on, and applied to different fields of sound, waves, and so on. He also developed quite a lot of summation of asymptotic series and super asymptotics, and the super oscillations is also one of his preferred recent direction of investigations. I think that the main features of Michael, as for any great scientist, is the curiosity. I would like to ask you to look for his paper about levitron, a levitation of frogs, which is very nicely written in funny papers. He wrote approximately 500 articles published and got about 60,000 citations. Michael is a doctor honoris causa for many different universities around the world. He got almost all possible and impossible awards and distinctions. The list will be too big to give here. In particular, he got very specific British distinctions. He was knighted in '96 for the services to physics. He is a fellow of Royal Society of London, of Edinburgh, and so on. So we are all very happy that Michael was accept our invitation, especially in this strange and difficult time. And I ask you to join me to welcoming him to start the talk. Please, Michael.
Thank you very much, Eugene. Thank you, Emmanuel. Can you hear me? Yes. Very good. And on Zoom also, I hope. It's really lovely to be back in Paris and to speak not only to people on Zoom, you are very welcome, but also to a live audience relatively unmediated by electrons. I really appreciate this invitation. Thank you. I also appreciate the help of the technicians here, an army of technicians who struggled to get the lighting right. But I notice that there's a slit of light coming. And if we had a large prism, we could reproduce Isaac Newton's experiment, because he also, if you've been to Isaac Newton's house, just a few 100 kilometers north of Cambridge, you can see the very window where he made a hole, and there was a slit of light, and he had his prism. But unfortunately, it's just a nuisance today. Nothing can be done, I think. It's the blind. What? It moves. Well, there's a slight wind. Well, it moves with the sun, indeed. So if you ever doubted the rotation of the Earth, now you can see the proof. Anyway, thank you very much again. Now, let me see. Good. So the title of this talk is Geometric Phases. And one aspect of this particular subject, which I want to emphasize, is that it connects a large number of different areas of science. And I want to quote something very beautiful from my late colleague, Charles Frank. Physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. And that's a very deep statement. We all enjoy these connections. They're not an optional extra. They're an essential part of the scientific process. Good. Now, this talk is a kind of intellectual sandwich. In the beginning, it will not be very technical. Then there will be a technical interlude, because I know that although many of you appear to be students, there are also people here who are experts on this subject, and then it will be, in the end, again, not technical. So this is the nature of the subject. I will mention very few names of scientists as I speak, but at the end, I will do so. I'll give you a timeline of the rather intricate history of this particular idea. So names will come. But first, there is a name. I want to go back to the first geometric phase in physics, discovered in the optics of crystals in 1830. And this was by Hamilton. We all respect and revere Hamilton. Theorists here will know that you can hardly write a paper on physics without a sentence like, consider the following Hamiltonian. We all know. By the way, I hope you don't mind if I'm sitting, because it's easier to control the computer for the Zoom people. So please forgive me for that. Right, Hamilton. Now, he knew that in a general crystal, two beams of light can travel with two different polarizations in any particular direction. And he knew a geometric construction called the wave surface in the space of directions. Technically, that's the Hamiltonian in momentum space. And this construction is a Fresnel wave surface. Here is half of it. And before Hamilton, the full structure of this surface for a general crystal where all three directions are different was not appreciated. And he understood, here is half of it, he understood this structure. There are two surfaces intersecting at 4 points on two optic axes. That's why these are called biaxial crystals. In these directions, the two polarizations have the same refractive index, the same speed. And Hamilton realized, looking closely in a very modern way, he realized that these intersections are singularities in the form of a double cone. This was the first conical intersection in physics. It anticipated others in quantum chemistry and in condensed matter physics, and they all have the same mathematical origin. But these points are degeneracies of something. There is a fashion in condensed matter physics of calling these Dirac points. That's actually a misnomer. They should really be called Hamilton points. You know, I'm from Bristol, and in Bristol, we certainly have the highest esteem for Dirac. He was born in Bristol. I sometimes show people the house where he was born, but this was Hamilton, not Dirac. Now, he found a way to see this intersection, and there's stuff oh, good. He found a way to see this intersection. Take a slab of this crystal and cut it at right angles to an optic axis and shine light through. And he made this prediction that the beam would spread into a hollow cone, slanted, it doesn't matter why, which would refract out into a hollow cylinder. And if you put a screen there, you would see a little ring of light. Actually, it's two rings. I'll show you in a moment. Doesn't matter. This created a sensation, and it was observed by Lloyd. And this is actually a simulation, but we have equally good experimental pictures of these two rings. And what Lloyd observed is that this light is linearly polarized, with the direction of polarization rotating by 180 degrees, pi, as you go around the ring. And I think that this is the first geometric phase in physics. I can't get rid of this black stuff at the bottom. Let's try that. That's a little bit better. There we are. It's a phase change of, why is it a phase change? These are eigenvectors of something, and a rotation is the change of phase. So that's the first geometric. So now, what are the concepts? Phase and geometry. Well, just a second. Well, what is phase? It describes the stages of any cyclic process. You know the phases of the moon. The cyclic process is the change of the shape of the moon. And of course, it's cyclic, so it's natural to describe phase with an angle. You all probably know that. Now, what about geometry? Well, the geometry is called anholonomy. It's parallel transport in the presence of curvature. Well, here's the curved Earth. And if I take a javelin, here I have one, it's my stick, there we go. If I take a javelin and I'm standing at the North Pole and I'm pointing it towards you, I then move down to the equator, there. And the aim of this game, I'm doing it again, is I never rotate about the vertical. I just translate it. And then I go, let's say, from the West Pole to the East Pole on the equator, if I may say so. Here we go. And then once again, obeying the rule, I lift it up again. And then I find that it's turned, although I have never rotated it. I'll do it again just briefly. I go down, I go round, I go to the North Pole again, and now you see I'm pointing sideways, and I started pointing this way. Okay, this goes back, I don't know about the demonstration, it goes back at least to Gauss. Now, the turn is the solid angle that the path makes on the sphere. Very good. It's global change without local change. Here in Paris, you have the Foucault pendulum. It's another example. It swings back and forth, but its plane of swing turns as the Earth rotates, driving the local vertical. Okay. Now, underlying parallel transport is something called, I used the word before, I use it now, anholonomy. Something returns after a cycle, that's the position of the javelin or the axis of the Foucault pendulum. Something else does not return, the orientation angle or the swing plane of the pendulum. I'll give you two examples of anholonomy. You know, if you drop a cat upside down, she turns. She has zero angular momentum, no torque is acting on her, no angular velocity, but she still turns through pi, and so now she has made a cycle in the space of shapes. She is not a rigid body. And that has enabled her to turn without ever having rotated. As I say, she's pursued a cycle in the space of shapes. Here's another example. Suppose you want to park your car and you have a very small place to park your car in Paris. I think this is very familiar. You find yourself having parked badly. You're too far away from the curb. So you make a cyclic series of maneuvers. You steer and you drive. They don't commute with each other. If they did, you could do all your steering in the garage before you left home. Okay, so you do this and then you do this, and then you find you're slightly closer, and the anholonomy is this sideways shift. It's actually an area in the space of driving and steering. That means that if you only have a small space in front, let's say size epsilon, you need 1 epsilon squared maneuvers. You always have to do this more often than you think. That's because of this geometry. Very good. Now, the geometric phase combines these two ideas, phase and anholonomy, in the physics of waves, optical waves, quantum waves, the like. The phase is of waves as they oscillate, and waves are very fundamental in physics, and phase is their distinguishing property, so you certainly should know everything about phase. The anholonomy is you cyclically and slowly, we come back to slowly at the end, change the conditions of the waves while they're oscillating fast. Okay. Now in light, that's changing the state of polarization or changing the direction. In quantum waves, it's cyclically changing the forces on molecules, atoms, neutrons, electrons, many examples. Now, I want to distinguish the dynamic phase from the geometric phase, because, you know, even if you don't do anything, a wave still waves. You know, this exponential of minus I omega t, the parameters don't change. But the geometric phase is the change, the extra contribution, the additional phase when you do change the parameters. Now, you can put it this way. After a cycle, the dynamical phase answers a question. How long did your trip take? The geometric phase partially answers the question, where have you been? So that's a quick way to remember the distinction. Now, it's phase, and so a natural way to measure the geometric phase is by interference. For example, in polarization optics, you have light, you split into two, beam splitter, interferometer, and you have here a stack of polarizers, and then you bring them together, you have fringes. This is to equalize the intensities to get a good contrast. Okay, well, if you twist the polarizers, then this changes the state of polarization and you shift the fringes by the geometric phase if you've arranged everything correctly. Good. How do you represent polarization? Again, something from Paris. We have the Poincaré sphere. Now, I'll just tell you what this is. And by the way, I won't have time to speak about it, but how Poincaré found his sphere is an interesting little episode in history, which you can read in his Leçons d'optique. Well, the North Pole is circular polarization in one sense, the South Pole is circular polarization the opposite way, the equator is linear polarization, and other points are elliptic. And you could make, for example, a cyclic sequence of elliptic polarizers by choosing the crystal slabs correctly. I won't go into the details of that. And the geometric phase is then half the solid angle that this path subtends on the sphere. I'll show you a couple of examples. Here's an untwisted stack of four polarizers. The prediction is that in this particular case, when you do the geometric phase will be pi, and here it is. These are millimeters, so this is a kitchen table experiment, which my postdoc Susanna Klein did. And again, if you take retarders, not polarizers, the same ideas apply. This time the prediction, the particular sequence was at pi on 3, and here it is. What is the difference here? Well, the difference is that polarizers are projection operators mathematically. They throw away half the light. Retarders are transparent, they're unitary operators. You can see both polarizations, but they're separated. Good. So, and the concept is the same. There are many, many examples of this. Neutrons, atoms, electrons, the Aharonov-Bohm effect, where you have a line of magnetic flux, electrons go on either side, and you see a phase shift. There are many, many examples. I wanted to make another distinction. When I wrote my paper in 1983, I used the expression topological phase. My colleague John Hannay told me, you mustn't use that expression. It's not topological, it's geometric. The difference is that it's geometric if the phase can take any value, like the solid angle. It's topological if the phase is independent of the path, provided it encloses something. The Aharonov-Bohm effect, you have to enclose magnetic flux. The pi phase including a degeneracy, like in conical refraction, as I showed you. So there's distinction there. Now, I want to describe what I regard as the deepest physical application of the topological phase. It's with Jonathan Robbins. And that's to understand the spin statistics connection. Now, the simplest example is the Pauli exclusion principle if you have spin half. In general, in quantum physics, you exchange two spins and you do get a sign if they're fermions, half integer, not if they're bosons, integer. So minus 1 to the 2s. Now, this is a long story, which I'm very, very brief about. Many people have tried to understand this Pauli principle in terms of ordinary, old-fashioned, simple quantum mechanics. The proofs are in field theory and relativity, but still, we think, and we'll explain how, there was something was missed in the attempt to understand this in terms of ordinary quantum physics. Now, it applies to identical quantum particles. That's the contribution of this piece of physics from Pauli to deep old philosophical questions about what it means for things to be the same. What was missing was building identicalness completely into the Hilbert space, where positions and spins, if you exchange particles or if it's more than two, you permute them, are identified. And this is a tricky technical thing to do. Exchange is a cyclic process, and the calculations lead to a topological phase 2 pi s. Just to show you why this happens. You have two particles. Doesn't matter where their center of mass is. Let it be the origin. R minus R. There they are. An exchange is R goes to minus R. That's exchange. But if the particles are identical, you must identify R and minus R. People had thought of that, but also you must identify the spin states, and that takes a little mathematical technology for identifying spins. Once you've done that, the sphere becomes a projective plane. For example, you can identify points across the equator. And then R goes to minus R is then a non-contractible loop. It's a topologically non-contractible loop. You're in geometric phase territory, and you can calculate the phase is this 2 pi s. Now, why is it that Robbins and I are not famous for having proved the spin statistics theorem? The reason is this. Our first calculation involving transporting the spins did lead to the known physically correct phase. But then we discovered later there are other ways of making this transformation which lead to the wrong spin statistics connection. Now there was something wrong, something unsatisfactory. Every one of these constructions that led to the wrong answer, but we were never able to find a mathematically convincing in advance specification, which led us to the construction that we first made, which seemed to us to be very natural. So we don't say we've proved the spin-statistics connection. We say we've contributed to the understanding of it. And that's all I want to say about that, but it is an application. Now comes the technical part for people who are hungry for formulas. So consider a quantum state, call it n, depending on some Hamiltonian, h, depending on some parameters, electric fields, magnetic field, whatever, and some circuit around which you take these parameters. What is the geometric phase? There are two expressions for it. Oh, by the way, in condensed matter physics, these parameters could be the components of the Bloch quasi-momentum vector living in the Brillouin zone. Okay, so here's formulas. Right, first of all, it's the integral of something round the circuit. Mathematically, that's called a one form. A one form is something, when you integrate it, you get a number, right? But you can also, using Stokes' theorem, write it as the flux of something through any circuit that bounds any surface of which the circuit is the boundary. Now, this thing is called the curvature, and it plays a major role in many applications. It's the analog of the curvature of the sphere, and this integral is what will then give you the solid angle. Now, something important is this. You can write it as a sum over all the other states in the system, not the one that you're transporting. And the advantage of this is that it tells you two things. The first is, it's obviously gauge invariant. Now, gauge invariant means the following. When you define an eigenstate of a Hamilton at some particular set of parameters, it can have any phase you like. It's arbitrary. It lives in what's called the projective Hilbert space. Doesn't matter about that. And this form, this thing you integrate is not invariant, although the integral is. But here, this curvature is invariant, it is gauge invariant, and you can see this because it only involves matrix elements of the Hamiltonian and the phases cancel. But more important, it's got this denominator, which shows you that you get a large contribution to energy from the states of the spectrum of the system, which are close to the state, the one you're transporting. Now, and of course, it has a singularity at the degeneracies of monopole type, inverse square. And this is what gives rise, for example, to the solid angle. You can think of a solid angle or a sphere as from a monopole at the center, and the flux of that is a solid angle. Very good. Now, I want to speak a bit about this curvature. I'm calling it B for a reason that will come later, and that's this thing. And it's equivalent, now comes a little piece of mathematics, to an anti-symmetric second-rank tensor field where these derivatives are with respect to parameters. Now, this suggests it's part of something more general, which is a quantum geometric tensor, which has this anti-symmetric part, which is imaginary, and it's therefore Hermitian, and it has a symmetric part. So what's this other part? Well, it's the quantum metric tensor. It's a way of describing how close two quantum states are. If you ask what is the distance between two quantum, one way of describing it is this. If the states overlap perfectly, overlap will be one, it will be the same state. Well, you look at the difference between one and the overlap, and that has a Riemannian structure, Gij, dxi, dxj, like in relativity. So this is the other part of this tensor is interesting. Now, I want to illustrate these ideas. I want to take 3 parameters, the 3 for a reason I'm not telling you, but it's natural, X, Y, and Z. And here are 4 n by n complex Hermitian matrices which I fix. So I can move about in parameter space and look at these quantities. Well, I do have to say why. Degeneracies are codimension 3. That means that to make quantum states coincide, you have to change 3 things. Well, here I'm only changing 2 things, so I won't see a degeneracy, but I get this big spike, which tells me that if I change the third Z, I should see a degeneracy. I'll show you in a minute. So that's near degeneration. This is the metric tensor. This is the trace of it. It's a simple way to describe it. It looks the same, but actually it isn't quite the same. Right. So if I would slightly move this value of the third coordinate, I should find a degeneracy. And indeed, I do. This is the length of the curvature considered as a vector, as you can with 3 parameters. Good. Now something else, recent work with Pragya Shukla. You know, it's interesting to ask when you have a concept in physics like the curvature, what are its general properties? So you imagine an ensemble of systems, infinitely many copies of that, like you do in statistical mechanics, and ask, what's the typical behavior? Is there anything you can that you can say? And one way is to look at the statistics of, for example, the length of the curvature vector. This is part of an endeavor that's come into physics, and it's hardly mentioned in the last 50 years, where we look at things that are typical instead of things that are special. It started in mathematics. They talk about structural stability. Physicists talk about genericity, universality. It came in simultaneously in wave physics, but also in physics of critical phenomena in phase transitions in statistical mechanics. So it's an idea that's come. Okay, well, what is this probability distribution? It's different for 2 states and for higher than 2 states, for a reason I won't go into. And these are it's a fat-tailed distribution, and that comes from degeneracies. And then there's a formula for it. Okay, well, what about higher dimensionality? Well, it scales with the mean, and the mean curvature depends on the number of quantum states in your system, and there's a formula. It doesn't matter what it is, but anyway, it's an understood theory, and you can test it. Take 10,000 sample Hamiltonians and calculate the curvature and look at the distribution, and it agrees fairly well. There's some slight theory, there are approximations in this theory, but it's more or less it's pretty good. Well, the same thing, look at the metric tensor. What about its trace? It's a little bit similar. I'm just showing you it for 2-state systems. And here there's a theory that agrees very well with observation. It behaves differently down near the origin, though. You see, the behavior near origin depends on the number of states. If it's an infinitely many state system, then faster than any exponent, and it's exponentially small, a particular form. Doesn't matter. This is recent work. We understand the typical behavior of these mathematical physical quantities. Now that's the end of the technical part. Now we go back. I want to talk about the dynamics of the parameters here, what I've called R. Now, the geometric phase results from a system being cyclically driven by changing parameters, fields, coiled optical fibers, whatever. But those parameters are physical variables as well. So the whole system, including its phase, must react back on them. There must be some effect. Now, normally, very often, it's not interesting. I mean, if I've got a set of polarizers and I rotate them, I'm not interested, or I could never measure, it would be too small. The reaction of the geometric phase of the light passing through on those parameters that I'm adjusting with my hands. If I have a big laboratory with big magnetic fields and sources to twist neutrons, I'm not going to see the effect of the phase of those neutrons reacting back on this big piece of apparatus. But sometimes you do need to consider this reaction. And in the physics of molecules, that's such a case. So you could think of a molecule as a collection of nuclei and electrons. The nuclei are heavy, they move slowly. Their coordinates position are the parameters. They drive the electrons, which are light and move swiftly. So you have this separation. Now, it's very common in quantum chemistry to use the Born-Oppenheimer approximation, where you say the nuclei hardly move while the electrons quickly solve their Schrödinger equation. And their quantum energy levels depend on the positions of the nuclei. Now, those electronic energies of the electrons act as a force field called the potential energy surface, in which the nuclei move while they slowly solve their Schrödinger equation for their own energy levels. These are the vibration rotation levels of the molecules. Very good. But the approximation depends on a separation of timescales, slow and fast. And when the electrons energies get close, so that transitions between them are slow, this threatens the Born-Oppenheimer approximation, and especially where they coincide at degeneracies. But degeneracies are precisely places where the geometric phases originate. So you can expect geometric phases to be places where Born-Oppenheimer breaks down. Here's an example, a 3-nucleus molecule, sodium 3. And here's a space of a certain class of shapes. And as the nuclear shapes make a circuit around a shape which is often symmetrical, where the electrons have a degeneracy, here it's triangular, the electrons gain a geometric phase of pi. Well, that means that this must be compensated by a pi, actually minus pi, it's the same, phase shift of the nuclei. So when you solve the nuclear quantum mechanics, you have to take that into account to make the whole quantum state single-valued. Well, this is a topological shift and it affects the quantum spectrum of the nuclei. Roughly speaking, you can't index the levels by a half. You have to index the levels by a half, 3 half, 5 half instead of 1, 0, 1, and 2. It's a kind of half integer quantization. And experiments were done where they showed that you actually can only index the levels properly that were observed if you take into account this geometric phase. And there are other examples as well. But pi is a special case. The more general geometric phase also reacts back on the slow physics that drives it. How? Well, this reaction, it's the first correction beyond Born-Oppenheimer, is a force of magnetic type, geometric magnetism, it should be called. It's on the slow variables proportional to how fast they're moving. Born-Oppenheimer, they're frozen, but they do move slowly, and this is what the effect on the slow variables is. Now, what is this magnetic, pseudo-magnetic force, geometric? Well, it's precisely the curvature. So that reveals that this object has a dual role. It's flux through a circuit, gives the phase on the electrons, and it also gives a magnetic field of geometric origin, which acts on the motion of the slow variables, whether that's classical or quantum, actually. Just another one little piece of mathematics. If you imagine the simplest coupled slow fast system, slow kinetic energy, fast Hamiltonian, depending on the parameters, x, I call them r before it's the same. Now, there you have the fast eigenstates. We would like to understand the slow motion. And one approximate way to do that is to take the expectation value of this for the given fast state that the system is in, the nth one. When you do that, you get the following slow Hamiltonian. In the kinetic part, that is, you have Born-Oppenheimer, momentum, and the electron energies. But then you've got this magnetic potential. That's the one form whose curl is the curvature. That's what I've told you. But there's also a scalar part, which depends on the metric tensor. So that plays a role as well. And it has a nice property, by the way. It's always repulsive when you're near a degeneracy. It acts to slightly protect the Born-Oppenheimer approximation. Good. Now, I will give you an example of that from the polarization rotation phase of light. I didn't describe this, but it's an experiment that was done. If you have a coiled optical fiber and you have linearly polarized light, the polarization is rotated if the tangent at the end is the same as the tangent at the beginning. It's a cycle in the space of shapes of the coiled fiber. And but the polarization is parallel transported, is rotated. Now, it's driven by the tangent along the ray. Okay. The geometric magnetism, if the fiber is free to move, it shifts the ray sideways, and you can see there's a slight shift in the beam passing down or in the fiber itself. And that was observed. So that's an effect of geometric magnetism. This was rediscovered in a number of different areas with different names: the spin orbit effect of light, optical Hall effect, optical Magnus effect, all the same thing, geometric magnetism. Good. Now, this mutuality, this driving of the fast by the slow and the reaction of the fast on the slow reveals something. The geometric phase is, in a way, it's an artifact. It's an artifact of our decision to consider a system in terms of its component parts rather than as a whole. If you would treat in a molecule the electrons and the nuclei on an equal footing, just put the Schrödinger equation into a computer in the spirit of quantum holism, all the physical predictions, the spectra, reaction rates, whatever, can be made without ever considering the phase. So does that mean the phase is useless? Well, no, it doesn't mean that, because first of all, it's computationally impossible to treat any but the very simplest molecule as a whole. So separation into parts is a useful artifact. But more important, exploiting this heavy light discordance is natural, and it leads to a physically understandable picture. So we don't want just to put on a computer outcomes. We would like to actually understand in some way what is going on. So it's actually useful. And go back to Isaac Newton, actually, if you really wanted to consider as a whole, you have to consider the whole universe, because nothing is completely screened from everything else. And of course, Isaac Newton emphasized you just get empty words if you try to consider the universe as a whole and understand everything within it. You say, I'm studying this, I'm not studying that. Now, this is important because this brings into mind the whole area of physics of a system and its environment. And there are a number of different classes of phenomena of that kind. You see, the environment might be perturbatively small, it's weak. That's a common case in a laboratory. What's outside is too weak to matter. Or it could be disorderly, it could be a heat bath. Or it could induce decoherence. Something very weak can nevertheless destroy quantum phases. Or it could be slow as opposed to fast. So this is a little bit of that much larger problem. It's a very difficult part because, this separation is an approximation. The geometric phase is an approximation, slowness. Geometric magnetism is the first correction beyond Born-Oppenheimer. Now, beyond the approximation, both the phase and the reaction forces involve infinite series of corrections. Now, for the geometric phase, we understand those corrections The series of corrections to the reaction force is much harder to calculate, and only a few beyond geometric measures are known. It's a very hard problem in theoretical physics. Both series almost certainly diverge. It's another lecture. Almost every series in physics diverges. You learn infinite series when you're at school and you talk about conditions for convergence, but most series in physics don't converge, and it's a very interesting area why they don't and so on, even in classical physics. Now, why is it hard? I can very quickly tell you. It's because corrections involve derivatives of the driver, where the parameters are, how their rate of change, their accelerator. But in classical physics, slow dynamics should give forces that depend only on the position on the velocity. And there's a subtle back substitution formalism that helps you get rid of this problem, but you don't quite get rid of it. It's still extremely difficult. And there's a key concept. I don't have time to speak about it. Good. So there's an unsolved problem, and it's important because it deals with the question, how strictly can you separate slow and fast? If the series will converge, you'll be able to write the slow dynamics in a way that works whatever the speed of the fast, but that's not the case. Now, bit of history. 1831. I mentioned Hamilton and Lloyd, the pi phase in conical refraction. 1924, Bortolotti showed that Maxwell's equations imply that polarization is parallel transported along curved rays. That was rediscovered by Ritov, and one of his students, Vladimirsky, in the year I was born, realized that parallel transport then means that if you could have a ray which coiled around and came back in the same direction, the polarization would rotate. Now, he didn't have optical fibers, and he said, I don't know how I can make this happen experimentally. Well, now you can with optical fibers. It was done. 1956, very important, Pancharatnam, brilliant nephew of Raman. He understood what we now would call geometric phases for two-state systems in the context of polarization optics. He emphasized a natural connection. That's what we would now call the one form. He didn't write it like that. Also, the solid angle if you change the polarization state of something. Very important paper. 1958, Longet-Higgins and colleagues, they realized in quantum chemistry the first step beyond Born-Oppenheimer, this pi phase of the electron states implies modification of the nuclear vibration rotation states. Energy levels of the nuclear. That was work done in Bristol. Also in Bristol, a year later, apparently unconnected to this work I've described, Aharonov and Bohm, the geometric phase for electrons from a line of magnetic flux, so no magnetic field outside, inaccessible to where the electrons are, but still the electron's phase is changed. And there's a long story about that. Again, it's another lecture, which I'm not giving. But they were also in Bristol. 1975, Budden and Smith, completely different area, radio wave propagation in the ionosphere. They realized that there's the phase is a kind of memory of the system. They call it phase memory. But then they found this additional contribution, additional phase memory. They didn't quite understand it, but their expression is exactly the integral of this one form along the ray. So it's related to geometric phases. It's a very important paper, hardly ever cited. 1979, another major paper, Mead and Trullard generalized Longet-Higgins by understanding, they looked at a little tiny cycle of the nuclei. They found what we now understand as the expression for the curvature, geometric magnetism. My paper, 1983, published a year later, well, I emphasized the importance of circuits. It was general in quantum mechanics, underlying the underlying two form, that was something I emphasized, and the fact that these arise naturally when you solve the time-dependent Schrödinger equation. And of course, I was in Bristol. But Barry Simon, who I told about this before it was published, made a very important contribution. He made a connection with the then newly understood beginning of quantum Hall effect in condensed matter physics, and connection with mathematics, fiber bundle theory, the Chern class, which counts the degeneracies which organize the geometric phase. Wilczek and Z, a year later, they found the counterpart of the geometric phase when what you transport is not a single non-degenerate state, but a family, because of some symmetry of degenerate states. There's the little matrix that comes back. The states, within the little cluster, the states can change their occupancies. My colleague John Hannay found if you have non-chaotic classical motion, the corresponding to the geometric phase of quantum physics is a change in the angle variables, in the action angle way of describing classical motion that's not chaotic. Aharonov and Anandan removed the slowness restriction because they understood what really matters is if the state returns, not what Hamiltonian you apply to make it return. Having a Hamiltonian and changing slowly, there's the adiabatic theorem, means that you will make the state come back. But if you just have the state, for whatever reason, returning, you have a geometric phase. For a long time, I didn't regard this very highly because I thought, well, what's a mechanism for making a state come back entirely, other than adiabatically? Now I know differently because from a different context, I found a way of making a quantum state change without transforming to other states arbitrarily fast. It's called transitionless quantum driving. That came because there were in laser cooling and there are times when you want to change a system quickly, but you still don't want transitions to unwanted states. And there's a way to do that. So this, I think, reinstates this as being a very important contribution. And then with John Robbins, as well as this spin statistics I told you, we looked at the rather awkward formulation, but I think right, of this classical analog of Hannay's angles, but for a chaotic classical system, not an integrable one. And now I work, for example, with Pragya Shukla, these high order reactions beyond von Oppenheimer, as well as the statistics of the curvature and the metric. Now, just to make a comment, a lot of the examples I go from Bristol, and there's a kind of geometric tradition which I sort of inherited without realizing it, which goes actually back to Charles Frank, who understood all kinds of what we now would think of as anholonomy, dislocations in crystals, disclinations in liquid crystals, which form the basis for what De Gennes, some of the work that De Gennes did here in Paris. And so there was this geometric tradition, not quite realized, but now we understand it very clearly. Well, what are you going to call this phase? It's quite common to name things after people. You know, the Schrödinger equation, Hamilton, Maxwell, fine. Perhaps you should call this the Hamilton, Lloyd, Bortolotti, Ritov, Higgins, Price, Erpich, Saka, Aharonov, Bohm, Budden, Smith, Mead, Trullard, Berry, Simon, Hannay, Wilczek, Z, Aharonov, Anandan phase. Well, I prefer descriptive terminology, which is why I call it the geometric phase. Okay, there's an interesting history, and I missed out some names, I'm sure. There were many applications of this. I can't resist mentioning one of them. It's the geometric phase of the stomach. What does your stomach do? It mixes your food. Now, if your food is fairly viscous, it can't mix your food by maneuvering back and forth. You know, your food mixer, the blade is a propeller that rotates, but biology hasn't so far developed rotations about an axis separated from the rest of the system. We don't have creatures that do that. However, these people realized that if the stomach makes a cyclic change which isn't self-reciprocating, in other words, a cycle in the space of shapes of the stomach, then mixing occurs. And they studied this in some detail, and I'm pleased to say that they adopted terminology I suggested. They should call it the belly phase. Okay. Now, I want to finish by going right back to the beginning. There's an easy way to see Hamilton's cone and its geometric phase. This is do-it-yourself conoscopy with Susanna Klein and Rajendra Bandari some years ago. And it's this. You use the fact that when traveling through the crystal, the two waves get out of step and can be made to interfere. Hamilton didn't do that. He used geometrical optics. It's a more difficult experiment. But if you have a black light sandwich, known in conoscopy, which is this. The bread consists of two polarizers oppositely. So that would be black, of course, because this polarizer would suppress the light that this polarizer allows through. That's the bread. That's a poor person's sandwich. But if you put in there something which is biaxial, then you should see interference effects and geometric phases. Well, what is a biaxial? For a theorist like me, I couldn't get a big piece of biaxial crystal, aragonite, for example, but the plastic that we used to use in our overhead projectors when we gave lectures before computers is biaxial. So that's the stuff you put in. We've all got boxes of this stuff that we don't use anymore, and almost all of them, for a reason I won't explain, are biaxially symmetric. You just put, what do you do with this thing? This centimeter square, you just look through it at any diffuse light, not the sun, the sky or clouds or a piece of white paper, and this is what you see. Now, these fringes here are the contours of the separation of the cones. I've aimed this, so one of the optic axes is in the middle, and it's centered on a degeneracy, which is a conical intersection. This black stripe is from a geometric phase pi. If the system were uniaxial, if two came together and two directions were equivalent in the crystal and has higher symmetry, then you would see a cross. Mineralogists know this. They use it to distinguish biaxial and uniaxial minerals. I have to tell you one other thing, though, is that every point on this picture represents a 2x2 matrix. In that particular direction, because looking is looking in different directions, in that particular direction, electric field EX-EY transforms into another electric field EX-EY, little 2x2 matrix, all of which have the property that they're non-trivial square roots of 0. Now, if you have a number, what's a square root of 0? It's 0. If you have a matrix ABCD, you can multiply by another matrix ABCD and get 0, 0, 0, 0. And all of these matrices are of that type, non-trivial. So just a nice comment. If you ever teach matrix theory, it's a good example of how matrices are different from numbers. Good. Well, I thought this was the end of this. I took some nice pictures. Here's the Atlantic from the west of Ireland, a little town where Stokes was born, a place called Screen. And again, you see the geometric phase, and it's striped nicely. I thought that was the end of the story, until I had a very nice message from two Dutch astronomers who said, no, from the trains in Holland, you look out of the window and you see the geometric phase in the sky. How's that? Well, what's a sandwich? The first polarizer is the sky itself. As Rayleigh showed, skylight is polarized as a result of Rayleigh's dipole scattering of sunlight from molecules that polarize in a direction 90 degrees away from the sun. So that's the first polarizer. What's the equivalent of my projector transparent? It's the window of the train, because windows of trains are stressed before they're installed, because if there's an accident, you don't want the window to break into sharp splinters. You want it to break into little blunt cubes. Another interesting piece of history which goes back 300 years, I don't have time to describe. So that's what about the final part, the analyzer? Like every good scientist, those astronomers carry a piece of Polaroid in their pocket and they look through. You see this. Now, blue sky. This was Rayleigh. I always think he looked like bank managers used to look like. In the old days when you would want a loan, you'd go. Now, of course, bank managers look like children, and you never see them anyway because they're at their computers. Anyway, Rayleigh, he was one of the very few people who was a member of the nobility, like Louis de Broglie here, independently of being a scientist. And that's where he lived and did his work, and he adapted his laboratory. Now, he died in 1919, and some of us had the honor in 2019 of being invited to the house of the present Lord and Lady Rayleigh to see Rayleigh's laboratory unchanged since 1919. It's slowly being catalogued, all the stuff there, a whole wing of this building, very beautiful. And I was able to hold in my hand his handwritten manuscript of the polarization and the color of the blue sky. Wonderful thing. So I wanted to see this from British trains, and indeed you can. Stop. And just to say something, I'm very happy to deal with questions, but I don't hear very well, and especially when people are wearing masks, so I can't help that. I hope you forgive me for taking mine off. I'll put it on again soon. But so you might need, Raul, you might need to translate the questions for me in case I don't hear. And that applies remotely as well. If you lower your mask, I have a better chance to hear you. Yeah, thank you.
Me. There is a trick well known by experimentalists where you send a polarization, for instance, vertical, you have a mirror like that, and then other mirror like that, and then polarization is turned to horizontal. Has it a connection with what you have explained, and what is a connection, please?
I will tell you. Soon after the geometric phase, the experiment with the coiled fiber was done by Chow and Wu. They showed they have a coil. And then almost immediately afterwards, there's a paper by Kitano and others, where they said, well, if you arrange a group of mirrors, like in an appropriate way with breaking chiral symmetry and so on, then you look at the two, each of the, this is not slow, but each of the polarization changes induced by the mirrors, if you end up with the ray coming parallel to how it was originally, the polarization will have changed, and they calculated the exactly the how the polarization change depends on the sequence of, or the orientations of the mirrors in the sequence.
Sure,
so it's a discrete version of the integral.
Yes, but this is what I wanted to say. Here, it's not even discrete. It's not small steps. It's a big step and another big step. So there is no hypothesis of slow motion or something.
Exactly the point. So that's an example. And then I wrote a little paper pointing out that this depends exactly on the conditions for the reflectivity at the surface of the mirror, and for ordinary metal mirror, that's it has the same effect as it does if you have a transition between two refracting media at the boundary of total internal reflection, total external reflection. So, thank you. But so this is, as you say, it's a discrete version. It's a little series of matrix transformations as opposed to an integral. I mean, basically, it's the same. But you correctly make the point that, as they made, Kitano and others, that in 1985, that this is a way of, as a kind of discrete. What's the phrase? It's a discrete sampling version of the continuous phase. So thank you. Yeah. No, okay. Thank you.
You said that integral of one forms play a crucial role. And what about higher forms, like 2 form, 3 form?
Well, the 2 form plays a role because you use Stokes' theorem. So that's where the curvature comes in. There will be analogues with higher forms. And to my knowledge, and this may simply be my ignorance, this has not been systematically identified, systematically implemented. Now, whether there is such a contribution and how it's related to phase of a driven system, I don't know. I'm slightly skeptical that there would be, but on the other hand, You know, there's Gell-Mann's totalitarian principle. Any mathematical concept related to physics will be found sooner or later in the universe. So I can't give you an answer to your question other than saying it's a very important question and it should be looked at. Yeah.
Thanks.
So my question is about the molecular geometric phase. Is it unobservable in general?
Is it?
Unobservable.
Well, yes, I describe, yes.
For Na3 is a particular case of...
Yeah, very important. Yes, someone who's looked at this is Raffaele Resta, and he makes the point that generally something can be observed, but it's not in any immediately obvious form, the expectation value of an operator. I made some comments about this actually before in the appendix of my paper, which was not really convincing. But is there an operator whose expectation value gives a geometric phase? This was your question, I think. Yeah. And I think the answer is no. And Resta, who's looked at this in much more detail in the context of polarization in solid state physics, that's not polarization, what I was describing, that he thinks that this is a new kind of quantity that can be observed, which isn't observable in the conventional definition. You can certainly measure it, so it's there, you know. But thank you for giving me the chance to mention this. Maybe you know the answer. I mean, maybe you're asking a question.
Well, yeah, because I think it's not unobservable.
Yeah.
Because as you were stating before, it's like it comes from our, so in the case of a molecule,
Yeah.
do you understand? Do you hear me?
Yeah, could you tell me?
Okay. Can you hear me?
Yeah.
Okay, fine. So no, what I think is that in the case of a molecule, we observe like the generalities between electronic states because it comes from our choice of describing the system split between electrons and nuclei, and it comes from our description. And if you use another kind of description, like for instance, if we use like diabatic states rather than what are called the adiabatic states, this thing does not appear. So that's why I was asking.
Do tell me.
So maybe we can discuss about it later.
Are you saying that, are you talking about the choice of basis?
Yeah.
Oh, yes. Okay, now that's actually very important. So, for example, I'll give you an example. I mean, this is part of a completely different lecture, but it's, if you have a slow Hamiltonian, then adiabatic theorem, you start out in an eigenstate and you remain in that state, but you don't quite remain. You make a little translation, which is exponentially weak. That's well understood, and it's understood in this way. Even though the system doesn't have any degeneracies, that's for real time. In complex time, there are degeneracies, and you can show that that's the origin of the exponentially small non-zero transition probability of being in the other state. This was understood for many decades, starting in the 1930s, but then especially by the Russian literature in the 50s, and understanding in general. But if you ask a different question, okay, exponentially small, but when does it happen? Then you must look at the time dependence. And then this is very sensitive to the basis in which you measure the states. Now, you can measure in the basis of adiabatic states, right? But you can also measure in the basis of slowness parameter corrected. It's a WKB series of states, are slightly different. And if you look in that basis, you find that the transition from 0 to exponentially small is very different. It's always small, but it's all the square root of epsilon, not of exponentially small. However, if you go to a particular order of this series, which is a divergent series, in fact, roughly speaking, if you go to the 1 on epsilon order, if epsilon is slowness, then you find that the transition occurs universally, beautifully compactly. It's an error function. that's how the small exponential appears. And this is a very general property of divergent series that I discovered in the 1980s. And this was the first application to the history of. Now, of course, what you will see depend on your choice of basis in which you measure. I mean, in the case of neutrons, it depends on how you, which polars you use to measure the quantum state of the neutron. So yes, of course, some things do depend, and that was one example. But still, geometric phase is still what I mean, okay, this came out of the following. I asked the question, what is the full quantum mechanical slowness series? Slowness is epsilon of a geometric phase. Well, the dynamical phase is of order 1 over epsilon. It's a big phase, the whole long time you've chosen. The geometry has the significance that it's independent of the time you chose, but then there are corrections, epsilon, epsilon squared. I calculated those, and I showed that the series diverges. It has to diverge, because if it didn't, there wouldn't be any, if there wouldn't be any transition at the end, you would still be in the same state. So since in quantum physics, time-dependent transitions are the way things happen in the world, as opposed to eigenstates, which are things, you could argue, I'm a little bit exaggerating, that if that series did not diverge, nothing would ever happen in the world. Okay? So this is my reaction to your question. And thank you very much for giving me the chance to say it. Yeah.
Thank you.
Yeah.
When you cited Aharonov-Bohm,
Yes.
you put into parentheses Bristol. Do you mean that they made their discovery in Bristol?
Yes, Bohm was a political refugee from the McCarthy times, because he was considered, rightly or wrongly, I don't know, to have been a communist. He was certainly a left-wing person. He left America and went to North America, went to South America, to Rio, and then the Americans cancelled his passport. Right, so he was a kind of refugee. He went to Israel, to Technion, where Aharonov was a student who wanted to study basic quantum mechanics, but Rosen of EPR said, young man, it's a waste of time studying foundations of quantum physics. EPR, it's all old history now, do some calculations. But with Bohm, he found a very sympathetic ear, because Bohm was interested. And when Cecil Powell in Bristol, who had got the Nobel Prize for discovering the pi meson, who was not a communist, but certainly a left-wing person, said to Bohm, why don't you come to Bristol and be a professor in Rome? Bohm accepted. He brought Aharonov with him, and they worked for 3 years in Bristol, and they went different ways. But the Aharonov benefit was the last thing they discovered in Bristol when Bohm was a graduate student. And if you look at his thesis, you can see, you can, you'll be interested in this story. If you look at his thesis, he thanks somebody, a person called Rosser, for some helpful advice. And I contacted Rosser, who's no longer alive. He was a professor near Bristol. And he told me the story that in 1959, a group of all the young theorists in Britain were at a meeting in Oxford. They met every year. He said it was very cold. It was at Christmas time. They had one small heater and they had to stand, whatever. And Aharonov was very excited. And he said, I'm sure that the vector potential has a significance independent of the field, but I can't think of a system to operate. And John Bell apparently said, why don't you think of a single line of magnetic flux? And Aharonov said, that's it. And went off and did the calculation with Bohm, and then they had the paper. So there's a history with Bell. I never checked it with Bell, because I think while Bell was alive, I don't think I knew this story. It came later. So, good.
Thank you.
Thank you.